Chairman, ladies and gentlemen. I must excuse myself because of this presentation. I am not a loved person on conferences because I am talking about mathematics and transformations and everything, bad things. But if anyone or most of the people here made a GIS project, and I think most person in this room has realized that if during the project you have some geo-referencing problem, this is because at the very beginning of the project this geo-referencing problem was not properly solved. So geo-referencing is the very beginning of the GIS, I think so, or from my point of view. In Hungarian language, we have an expression: we start from the oven, from the stove, because in the dancing school, the new dancers couldn't properly dance, but they went back to the corner of the room, to the stove, and started from the stove, and the dancing went okay. So we start from the stove. Well, the content of the presentation. Why or geo-referencing? We will somehow overview the map projection transformations. We try to answer the question, why do we need correction grid, what I propose now. I will tell some words or some sentences on the evolution of correction grid standards, so how this standard of GSB files or NTV2 format developed. We see how this correction grid looks like, and we will have an example how to generate your own correction grid. Okay, map projection transformations. This is our very favorite figure. If you have two coordinate system, there is the direct method to convert from one coordinate system to another. You have easting and northing, E and O, easting, northing values in one coordinate system, and you want to transform then easting, northing values to another one. Then you might use, and H is the elevation above reference level, ellipsoid or geoid. You can use direct methods to convert between those two coordinate systems. For example, affine or polynomial, linear or quadratic transformation or triangulation between known points, so-called GCPs. What is the advantage of this method? If you have quite enough number of control points, then you can define a very fine structure to convert, so you can convert with high accuracy, and it's quite simple and supported by most of the GIS software. The disadvantage of these direct methods is this is suitable usually only for local transformations. You mean transform one map sheet to another, or transform different type of coordinates on a local area. And the other disadvantage, it requires many ground control points if you want to have a high accuracy transformation. The other method applied in GIS software is the transformation between ellipsoid coordinates. The black arrow downwards is the inverse projection equations. You transform the projected coordinates into ellipsoid coordinates. You have a 3-parameter so-called Bolodensky transformation to transform from the ellipsoid coordinates of one system to another, and you transform back to using the second system projection equations back to the projected coordinates. This figure implies that the ellipsoid coordinate of one point on the surface is not unique. It depends on which geodetic system it belongs to. For example, the ellipsoid coordinate of this point is different on the Romanian national system and different on the WGS84 coordinates. I will tell something on this problem. The advantage, it's supported by GPS. This 3-parameter transformation requires only 3 parameters for a large area, for a country, for example, and valid for a whole region, as I mentioned. The disadvantage, it has low accuracy. It is as accurate as the geodetic background of the projection systems. Okay, the third method is the transformation between the so-called geocentric coordinates. We place a coordinate system in the mass center of the Earth, and we transform these ellipsoid coordinates. Phi is latitude and lambda is longitude to these x, y, z orthogonal coordinates, Descartes coordinates, and we use a so-called Bursa-Volt transformation. This is a three-dimensional similarity transformation where there are dx, dy, and dz, the shift of these two coordinate system origo, and alpha, beta, gamma are rotation angles around this axis, and kappa is so-called scale factor. Okay, the advantage is the accuracy. It's better than the 3-parameter solution, a little bit better. And the disadvantage is the same, the accuracy. It's better than the 3-parameter, but not as accurate as we expect usually. So it's not suitable for geodetic purposes in the case of modern coordinate system. I can tell an example of Hungary. We have our national coordinate system, the EOV system. If you use this 7-parameter transformation to the WGS84 UTM GPS coordinate, globally, if you have a 3-parameter solution, you have average error of 1 meter, If you use a 7-parameter, the average error is ½ meter, and this ½ meter is not enough for geodetic purposes. If you have a look at on old map solutions, for the first military map of the Habsburg Empire, you have an average of 100 meters, but you might have 500 meters or 1 kilometer error for whole Kingdom of Hungary map series. One more important thing. When I mentioned first projection, we always believe that if you have a series of map sheets, like the first military mapping of the Habsburg Empire, and in one map sheet you have, for example, the Stephansdom in Wien, and you know it is 6,000 fathom times 4,000 fathom, the size of these map sheets. Then we can reference one map using the coordinates of these map sheets on the first projection system. First, we don't define the coordinate system, but we follow the coordinates what can be recognized on the map sheets itself. So we have, for example, 3000, 2000, 3000 minus 2000, and so on. Just this is a remark. Okay, why do we need correction grid? We need correction grid because the ellipsoid coordinates transformation is not a closed form transformation, not accurate enough. Why it is not accurate? Because it's an outcome of the geodetic system. How a geodetic system is generated. When you start measuring a country, you define geodetic base points, you make triangulation between these points and a baseline, so calculate you somehow the distances of these base points. Sometimes they made astronomic measurements on some of these base points and made the adjustment of the network. It's a least squares adjustment, and the outcome of this adjustment is the ellipsoid coordinates of that network. But these ellipsoid coordinates are similar to the astronomical coordinates of the base points, but just only on this area of the Earth's surface. So this adjustment is somehow local, and this is the problem. The other problem, but this problem can be handled with the 3 or 7 parameter transformation. The most important problem is the measurement errors. If one angle is measured has a blunder, a gross error, then these erroneous measurements influence the outcome of the geodetic work. So the base point coordinate would be wrong in one system, would be wrong. And practically the old geodetic system, especially in the case of the first and second, and also the third Habsburg military empire mappings, are full of this kind of errors. So the geodetic base points are erroneous in their own system. And these errors introduce an error in the mapping. It means the map sheets are somehow shifted a little bit. Okay. So we need a correction grid to this to rectify this problem locally. A correction grid locally makes a correction. If we can go to the next slide. The evolution of the correction grid standard. The first when they realized they required a correction grid was during the 80s, when in the US the North American datum 83 was introduced, practically because of the GPS measurements, but they had before the North American datum 27 and all the maps in that old coordinate system that had local errors, and now, at that time, they had to transform with geodetic accuracy up to 10 centimeters accuracy between the old mapping and geodetic system to the new GPS-based system, and they introduced the not-con conversion. If you use geodetic software, sometimes you see that you can choose the not-con conversion for geodetic datum conversion, but this is only valid for the US. Canada imported this system, somehow modified, and called it National Triangulation version 1, National Transformation on French, version 1 for Canada. They used only one file, not one file for latitude and for longitude as in the NatCon, but they put things into one file and defined that if on grid nodes you have a shift value, then in between these grid nodes you definitely use a bilinear interpolation to find out how much shift you have to be applied on a given point. And NTV2 is a new version. It's use a binary file. The extension of the file is GSB. That was in the title of the presentation. And it also has subgrids. It means if you have one grid for Canada, but if you have a much more detailed grid in, for example, for Toronto, the grid of Canada is 1 degree latitude longitude, for example, but you have 1 minute or 1 second grid for Toronto, then this one file can contain 1 large grid for Canada and 1 small grid for Toronto in the same file. And this format and this standard was used by Australia and some other countries, and practically this became an international standard of correction files. You can memorize the slide until I do. Okay, how does this correction grid look like? As I mentioned before, this is a binary file, but fortunately there is an ASCII format. We see here the header. There is a general header, 11 lines, means transformation between which datums, semi-major axes, and so on and so on. What is a general information? The next 11 lines is a subgrid header. It means it also contains the southern and northern latitude, eastern and western longitude. The surprise is the eastern and western longitude are minus numbers because it grows westward. It was invented on the western hemisphere. And all these values are in arc seconds. The fourth line is the angle type is seconds, arc seconds. And latitude and longitude increment is 180 seconds, means approximately 5 to 10 kilometer grid size, and number of points. And the next section is the data. In this case, it's altogether 8,319 points. It is sorted from bottom right corner of this data set in lines up to the top left corner of the data. First is the first column of the data is the shift of latitude. The second column is the shift of longitude, and the third and fourth columns are standard deviations, errors. This is important because if you have more subgrids and the software realizes that your point to be transformed in can intersect more subgrids, then it uses the smallest standard deviation value. So it's a quite intelligent software solution. Now let's have a look at how can you generate your own grid. First you use your uncorrected map and define projected coordinates, as I mentioned on this figure. And first define this coordinate system locally, don't care too much about it. And you must define ground control points on this system. So you have, for example, in this case in fathoms, an easting-northing system, and you have ground control point coordinates on your unreferenced, uncorrected map, and you find the same points on the reference map, and
Towards the computer.
I don't touch it. Face it. Okay, sure. Okay. You must find out somehow the map projection and ellipsoid of the uncorrected map. This requires some knowledge of old projection systems, or you go to library and read old papers somehow, or you ask us. This is another method. In the case of military, Habsburg military mappings, the Cassini-Soldner, the polyhedral projections are used, and the ellipsoids are Zach, Oriani, and Balbec and Bessel ellipsoids. So, okay, I can learn. And you can define the map projection and the ellipsoid in your GIS software. It's usually adding 1 or 2 lines to the description files. And you can, using these methods, you can calculate the ellipsoid coordinates of this control point. Okay. And you calculate the difference. So on the reference map, in modern coordinate system, and on the uncorrected map, the ground control point ellipsoid coordinate differences, and interpolate to a grid. We use software or GDAL for this. You have to sort the list on the format as I showed before, edit the header, and convert the ASCII data format to a binary grid using GDAL or GDI free-to-available software. Okay, we generated a grid for the third military mapping, the 1 to 75,000 Spezialkarte set, using the Ergebnisse data. This is a data set where that's the problem with the third military mapping, that they started the geodetic work around in the middle of the 19th century, but the army had decided to start making maps before the geodetic network was properly adjusted. So the map sheets has 200-300 meter shift long. But in 1902, they made the geodetic adjustment of the geodetic network and published the data set. This is more than 600 base geodetic control points that has a good system with no or minimal errors, and we also identified these points on maps. So we got uncorrected map coordinates and corrected map coordinates. We generated a triangulation, and we sampled this triangulation into an equidistant grid and generated a grid shift file. I show this visualization of this correction file for the former Kingdom of Hungary for the third military mapping. You see this, originally these map sheets were somehow adjusted in blocks. So you see left-hand side large shift, center no shift, southeast no shift, and so on, and southern part large shift. Thank you very much for your kind attention.